annoying that P is always late?
Yeah, I mean, when's he going to get here?
Yeah,
always,
like
Sorry, I'm late! Phew.
That's close.
Hey guys, welcome to the first lesson on circuits, and in particular on capacitors, as you may have gathered from the sort of title animation here. So at this point, what you should have in front of you is obviously this video, since you are listening to it, and your notes packet. What do I need my notes packet for, Miss Jericho? Well, because all of these questions that are going to be appearing on the screen in something like a video format are going to be prompts from your notes packet. So if you haven't printed it out yet, pause the video, go print it, have it in front of you, or whatever, have it in Notability, but on a separate screen, okay? I don't want the screen divided. It will be much easier to take notes if this is nice and big so you can read it well. Okay, so to begin with, the first question being asked is, what is a volt? All right, so a volt is the unit for electric potential, as opposed to potential energy, which is measured in joules. So they are related concepts, as you might have gathered from the names. However, potential energy is obviously not the same thing because it's measured in different units, and there's a different word for it. So potential is, as you can see on the screen, a joule per coulomb. All right, now exactly what is that all about? Well, it's sort of like how force is measured in newtons, but an electric field was measured in newtons per coulomb. All right, so I mean, you can see sort of maybe I should have written these on opposite sides here. You can see how the unit for electric field being a newton per coulomb is rather like this being a joule per coulomb, right? That's all I'm really trying to say, okay? All right, now continuing the analogy, if a volt is a joule per coulomb and an electric field is a newton per coulomb, then it follows that if I express the units like, or not the units, but the symbols for those things like this, where U is the symbol for energy, all right, and F is the symbol for force, all right, and then of course coulombs in both cases is charge. Well, I could rearrange those equations and get that force is, well, QE. Well, yeah, we should remember that one. And also that energy is Q times V. So that means that the energy that you have in, say, something like a battery, right, a voltage source, is charge times voltage. So it's not just the volts of the thing, it's related to the volts and how much charge actually moves through something. So then, which of these things here is energy? Which of these is the energy stored in a 9-volt battery? Sorry, this is actually a trick question because none of them are right. In fact, the energy stored in a 9-volt battery is 9 joules per coulomb, that's 9 volts, times the number of coulombs that the battery actually moves. All right, now I'm jumping the gun here a little bit. We're going to talk about what is electricity. It's charge moving through a wire, okay? So when something, whatever it is using electricity, meaning that there is electricity flowing through it, okay? The energy or work done by a battery over a particular amount of time is related to the volts of the battery and the charge that it actually moves through the circuit over that time interval, okay? So 9 volts isn't an amount of energy. It's only an energy if I take it times coulombs, because joules per coulomb times coulombs is what's going to give you joules. All right, so maybe the next logical question is, what does a battery do anyway? Well, it pushes charge around. That's fundamentally its purpose, right? So there's a simple picture of a battery, right? When I draw a battery in a circuit diagram, that's the symbol I'm going to use for it. I may not always write the plus and the minus, but the long line represents what's called the positive terminal on the battery, and then the short line is the negative terminal. If you're looking at an actual, like, let's say, D-cell battery, the bumpy side is the positive side, right? And then the flat side would be the negative side. All right, now if I put a battery into a circuit like this, you have to think about the wire. This is a picture of a light bulb, right? You know, wires, battery, whatever. You have to think about the wires as being full of electrons, okay? And so what the battery does is it pushes that charge around, right? It makes it flow, okay? Now, normally, we'll talk about direction of flow of charge in a little bit, but in fact, what would happen here when I hook this up is the electrons would flow in the direction that I showed there, and that would make the light bulb light up or the fan turn on or whatever it is you're trying to power exactly. All right, but as soon as you open a switch, like, you know, flipping a light switch literally, what it does is it breaks the connection between the power source and the thing that you're powering. And then no more electrons flow, and so the thing turns off. I realize your house doesn't run on batteries, but whatever. The principle is exactly the same. All right, now, related to batteries, we have this term which will come up a lot more later on in the unit. It's EMF, electromotive force. And it's that there's a funky symbol for it, which looks like a backwards 3. And if you're thinking, how do I pronounce that you say EMF. When you look at that, you shouldn't say what letter is that or anything, or E. Don't call it E. It's not E. It's pronounced EMF. Well, that's it. And what the EMF is the volts provided by the battery. Okay, so the EMF, electromotive force, of a 9-volt battery is 9 volts. That's all that really means. The word force in there, of course, is used sort of in an analogistic way, meaning it's not like volts are force. Volts are definitely not force, but by analogy, they do kind of the same thing. They do push charge around in your circuit. All right, now, how does a battery do that? Well, the answer is chemistry. It operates on chemistry. So, for example, if I have a nickel-cadmium battery, it operates based on this exact chemical reaction. All right, I mean, so a lot of this stuff, honestly, this is just for fun. You don't need to know all this chemistry that you probably forgot from last year. But I do want you to see that, oh, hey, actually it has bearing in other subjects like physics. So the oxidation reaction and the reduction reaction involve the exchange, or I should say half reactions, involve the exchange of electrons, right? The cadmium is losing 2 electrons, and it's giving 2 electrons to 2 different nickel atoms. And, you know, that results in them changing charge from 3 plus to 2 plus, while the cadmium went from being 0 to 2 plus. That's the reaction that powers a nickel-cadmium battery. You guys have seen some chemistry before. You know there's energy in chemistry. Well, this happens to be chemistry with a lot of energy in it, where you can conveniently store the 2 things that are reacting separated from each other, right? You guys talked about voltaic cells in chemistry, I'm sure, and drawn below is a simple voltaic cell where you have the reduction reaction on one side and the oxidation reaction on the other, and in between is a wire that connects the 2 sides. Now, since the reaction occurs through the exchange of electrons, well, electrons will flow through that wire. And also, technically, we have to also have positive ions that flow, whatever. You can't end up with excess charge accumulating on one side. That's not maybe the interesting part for most people. It's the, oh, look, there's electrons moving through the wire. Okay, so with the electrons moving through the wire, the reaction goes forward, but also, if I were to put something on that wire, like a light bulb, it will now turn on. Cool. All right. Now, what you may have missed seconds ago was, this is just for fun. You did not, or that part was just for fun. You don't need to know any chemistry, okay? But I thought it was an interesting thing to mention. Now, I want to talk about, what does it mean when we say charge a battery? Because that's a term that gets thrown around a lot. Does it look like this? No. No, it does not. When we charge a battery, we are not adding excess charge to it. Your phone doesn't become charged when you charge the battery in it, okay? It doesn't have an excess charge on it like you do when you, say, stand up off of the couch and triboelectrification occurs. Rather, when we charge a battery, again, it relates back to this chemistry idea, where if this is the reaction, initially you have lots of your reactants and none of or a little bit of your products, okay? But as time goes by, they get used up. A dead battery, you have none of your reactants, or very little of them, okay? And then lots of your products, and then the reaction's over. It's boring. No more chemistry happens until you supply a charging voltage and regenerate the reactants that you started with. That's what happens when you plug it in, is it reverses the chemical reaction. So let's have a little bit of a quiz again. Charging a battery means which of the following? Yeah, none of those. No, nope, come on. It means reversing the chemical reaction that powers it. It doesn't mean building up charge or losing or gaining electrons, right? All of that stuff is bogus. Your phone doesn't literally become charged when you charge it. Rather, you just reverse a chemical reaction. Now we're getting into the meat of it here, right? What exactly is a capacitor anyway, right? What is it for? What does it do exactly, right? What is all this stuff about anyway? Well, a capacitor stores charge. That's what it does. You can see here I drew two parallel plates, pieces of metal, which are attached to a battery. And that's pretty much what a capacitor is fundamentally, is it's two plates, two metal plates that are a certain distance apart, and you hook them up to a battery or something, and they store charge and therefore also energy. Technically, the total charge they always store is zero, because each, you got a positive plate and a negative plate, technically, but we will still say that they store charge. So next up is, what is capacitance, which is a very important unit. And so there you can see that it's measured in farads, the letter F. Please note in that equation the C is capacitance, not charge. Rather, the Q is for charge and the V is for volts. All right, now that means that a farad is a coulomb per volt. So down there I drew a little 1 microfarad capacitor, which means, based on those units, if it's a 1 microfarad capacitor, for every volt you put across it, it will store 1 microcoulomb. Okay, fine. There are bigger capacitors, right? There's a few more. I got 1,000 microfarad and a 4,700 microfarad. And then up there, what is that mysterious green one? Why, son, that is a 1 farad capacitor. It is a beast of a capacitor, because for every volt you put on it, it stores a whole coulomb of charge, which of course is a fantastic quantity. And now the final equation for this video, before we break to an example problem in the next video. This is the equation that you use to determine the capacitance of a capacitor. So we've got all these different quantities in there. Now I'm running out of time for this video, so what I'd like you to do at this juncture is take careful notes of what you see on the screen, pause the video, write all this down, and I will talk about all the rest of this stuff in the next video where I work out example 1. And I'll tell you what all these things are in that example.